Okay, so in this video we're going to be going over Unit 8 Worksheet 5 quiz review. Before we even get into it, most important thing here, make sure you're good on your naming, make sure you're good on writing formulas, make sure you know all your polyatomics. I gave a version of this quiz already to two of my classes. Biggest problem I saw was people couldn't write the initial formulas correctly, so they either couldn't balance them or they got the wrong molar masses. So again, know your naming. I mean, it should be learned by now. Alright, number one. So we're producing 7.2 moles of calcium nitride from the reaction of calcium phosphate and aluminum nitride. So calcium phosphate is going to be Ca3PO4 2, and this is going to react with aluminum nitride, ALN. And let's see, calcium is going to react with nitrogen. By the way, for this quiz, we're assuming it all goes through. I just kind of made these up. I didn't look at a solubility chart, so again, for this test, we're assuming they all go through. Calcium mixes with nitrogen, so Ca3 and 2, plus aluminum phosphate, which is just AlPO4. Okay, we need to balance it, so let's see, 3 calciums, 2 phosphates, 1 aluminum, 2 aluminum, so 2 there, and then N2, so we're good. Mole ratio of 1 to 2 to 1 to 2. So the problem tells me I produce 7.2 moles of calcium nitride. 7.2. How many moles of aluminum nitride must have reacted? So there's my X. And since I'm looking for moles, this is what I call a moles in, moles out problem, or just a mole ratio problem. Very easy. We don't have to do anything with grams. 2 over X equals 1 over 7.2. Cross multiply, so you get 1x equals 2 times 7.2. So that's going to be 14.4 moles. But you can see I only gave you 2 sig figs, so we're going to call it 14 moles. And that's moles of calcium nitride. Oops, I'm sorry. Moles of aluminum nitride, that's my X. ALN. Alright. By the way, type of reaction, double replacement. We have 4 species. Calcium, phosphate, aluminum, nitride. Switch places. Number 2. We're going to perform a reaction between 92.4 grams of magnesium nitrate and excess potassium metal. Alright, so I need to write my reaction out. So we're going to get magnesium nitrate, which is this, plus potassium metal, we just write K, because remember all our metals just appear by themselves. So the type of reaction here, single replacement. Potassium is going to try to bump out magnesium, and again, we're assuming that it does. Now, in fact, I know that it does do that, because group 1 always bumps group 2. So the potassium is going to bump the magnesium, forming potassium nitrate. And magnesium is out on its own, balancing this out. 2 nitrates, 2 potassiums, 1 magnesium, and my mole ratio, 1 to 2 to 2 to 1. Alright, so this is going to be a grams in, grams out problem. So I can't just write 92.4 here and just find my X, because this is a mole ratio, not a grams ratio. So I'm going to work out the calculation. So 92.4 grams of MgNO3 2 times 1 mole over the molar mass. So it's going to be 24.305, that's magnesium, plus 2 nitrogens, so 2 times 14.007, plus 6 oxygens, so that's going to be 96, 16 times 6. Alright, so it comes out to 148.32 grams. Gram cancels gram, and we get 92.4 divided by answer, 0.663 moles of magnesium nitrate. Big piece of advice for the quiz. don't just write the number. Take the extra 5 seconds to write the unit and the unit of what, because a lot of times you're going to get very confused. So this is now going to go up here, 0.663. And what are we trying to solve for? How many grams of potassium nitrate should be produced? So here's my potassium nitrate, here's my x. So 1 over this equals 2 over that. Cross multiply, x equals 2 times that. X equals, we'll put it down here. Let me do it up here. 1.25. And the unit there is moles of potassium nitrate. The problem is asking for grams, so I got to do another conversion. So potassium 39.0983 plus nitrogen is 14.007 plus 3 oxygens is 48. So this becomes 101.105 grams per mole. Notice I flipped this around from before because now we're canceling moles. And this becomes 126 grams of KNO3. All right. And we already did type a reaction. So now question 3, I performed the experiment above, and I got 112 grams produced. What is my percent yield? Well, percent yield is the actual over the theoretical. So in other words, what this number here represents is in this perfect world with no such thing as error, if you reacted 92.4 grams of magnesium nitrate, you would get exactly 126 grams back out. But we don't live in that world. So in the real world, you got 112 grams. So it's 112 grams divided by 126 grams, and turn that into a percentage. 112 over 126 is 0.888, repeating forever. So we're going to turn that into 88.9% three-sig figs, just like that. That's number 3. Number 4, mica table problem. Okay, a combustion reaction occurs between 77.0 grams of C3H6 and 249 grams of oxygen gas. C3H6 plus O2 yields CO2 plus H2O. First thing I'm going to balance are my hydrogens. So I have 6 here, so I would need a 3 here. The more I do these, the faster I can sort of look ahead. If I put a 3 there, I'm stuck with 2 plus 3 oxygens. I can't have that because I can't have an odd number here. So instead of 3, I'm going to double it and put a 6. Okay? Now let me readjust my hydrogens. So now I need a 2 there. So hydrogens are good. Carbons, I have 6. So a 6, we're good. And now as long as I have an even number of oxygens, we're good. So 6, that's 12 oxygens, plus another 6 is 18. So 9. 2966, and that's my mole ratio. So I can just rewrite it here. All right, so we have 77.0 grams of this. So let's work that out. 77.0 grams of C3H6 times 1 mole over. Carbon is 12.01, so times 3 is 36.03. Hydrogen is 1.008 times 6, 42.078 grams. Gram cancels gram. So this is 1.83 moles of C3H6. Now I also need to turn my other one into moles. So I started with 249 grams of oxygen gas, which is a Brinkelhoff, O2, times 1 mole over, this is important here, 2 oxygens. So instead of 15.999, or instead of 16.00, it's 32 grams. Gram cancels gram. 249 over 32 is 7.78 moles of O2. So we converted grams to moles. We're now going to plug this back into our grid. So 1.83778. 1.83, 7.78. So now we need to say which is my limiting reactant. Now at this point you might just think, well, clearly the one that's like 5 times less is limiting reactant. However, look at the mole ratio. For every 2 moles of this, we need 9 moles of this. So in fact, it might work out that this one runs out first. So the only way we can test this, well, there's a few different ways, but the way we have been practicing is I'm going to pick one of my products and I'm going to see how much I could generate using just that individual reactant. So assume the other one is in excess. And whichever one gives us less, that's our limiting. So we'll start with this. So using 1.83 moles of C3H6, how much CO2 could I get? So it's a 2 to 6 mole ratio, or a 1 to 3. So I could just multiply this by 3, or just work with the x. So 2x equals 3 times this. So it's going to be 5.49. Okay, so here's what I'm going to write. And this is important. Using C3H6, we're going to get 5.49 moles of CO2. Now I have to check with the other one. So if I had this much oxygen and this was in excess, how much CO2 would I get? So using O2, so this time we have 9 over 6, or 9 to 6 mole ratio. So 9 over 7.78 equals 6 over x. Cross multiply, so it's 9x equals 6 times this. So 6 times 7.78 divided by 9, 5.19 moles. Okay? So now you could see that even though there's a lot more of this, they're pretty close in terms of what's going to react. So now I can see that using my O2 I produce less CO2, so therefore my O2 is going to run out first. So what we can write is O2 is my limiting reactant. By the way, make sure you don't go like this and say limiting reactant, because I don't know what you're referring to. Yes, this one's smaller, but the limiting reactant is which one of these two things is going to run out first. So don't say like CO2 is a limiting reactant. In this case, O2 is limiting reactant, and because this one's larger, C3H6 is my excess reactant. So parts 1 and 2 are done. Step 3, or letter C, complete a mica table. So for the mica table, we start by rewriting our formula. So C3H6 plus O2 yields CO2 plus H2O. And rebalancing, so what did I have? 2966. So the M is mole ratio, initial, change, and after. So the mole ratio we already know, 2, 9, 6, and 6. And the initial we already know. We already did a lot of this stuff. So initially we had this many moles of each. 1.83, 7.78. And how much of our products? 0. This is before the reaction takes place initially. For C, which is our change, we now need to figure out how many moles of these were consumed, how many moles of these were produced. So the first thing we do is look at which one's our limiting reactant, which was O2. So this is going to get completely used up. Minus 7.78. And again, this is moles. Everything here is moles. So after, we're going to have 0 left. Okay? Now, we already figured out one of these. So, using O2, make sure you use the limiting reactant one. Very important that you use this one and not this one. We got 5.19 moles of CO2. So that's what we're going to write here. 5.19 moles. Yep. Okay? So this gives us a total of 5.19 moles. Now we have to fill the others in. So the thing to look for now is shortcuts using mole ratios, meaning if it's the same number, it's going to produce the same number of moles. So right here, I'm seeing a 6 to 6 mole ratio, or 1 to 1. So for every mole of CO2 produced, you must get an equal number of moles of H2O. So therefore, 5.19 produced over here gives me 5.19 moles produced over here. So you're going to get an equal number of moles of each of the products because of this mole ratio. Okay, now over here, we don't have a shortcut. There's no other 2. So therefore, we're going to have to do some math. Alright, so there's several ways you can go about this. I think one of the easiest ways is to use one of these as opposed to using your limiting reactant. But what's important to note here is that we're going to temporarily ignore this number because 1.83 is not how many moles are going to react. It's just how many moles like you have in total. Remember, that's the limiting react, or that's the excess reactant. So not all of that is going to be needed. So when we find the change, we're going to see exactly how much of this had to be used in order to react all of these amounts. So this is going to become our x. I'm just going to make that temporary because we don't care that we have this much. We want to see how much we actually needed. So you can use the ratio with any of these numbers that you want. So 2 over x equals 9 over 7.78, or 2 over x equals 6 over this, or 6 over that. Let's just choose this since it's closest. So 2 over x equals 9 over 7.78. Cross multiply. 2 times 7.78 equals 9 over x, not this. So that's divided by 9. Gives me 1.73, which I'm going to put right here. Okay? And let's just, I always pause to make sure this seems about right. Okay? Now, we said before, I mean, which one came down to the limiting? It was very close. You know, either one of these really could have been the limiting. So it makes sense that almost all of this was depleted. Okay? Now, by the way, you could have come up with this number using this as well. So let me just run that calculation just so we know. So it would be 2 over x equals 6 over this. So 2 times this is 2 times 5.19 divided by 6 gives us the same number, 1.73. Okay, so we're going to do the math here. You can see it comes down to 0.10 moles. And that's our mica table. So one thing you always want to check for is that down here, you should have one of these completely depleted. You should have a little bit of one of your excess reagents left. And then you should have a certain number of moles of product. Okay? Final question, I just tell you to convert these into grams. So letter D, how many grams of the limiting reactant are left over? I probably meant to say excess there, because limiting reactant is definitely 0. But assuming I ask you excess reaction on the quiz, we're just going to work this out. So let me look ahead to what I did. So this was my molar mass here. So we found 0.10 moles of this times 42.078 grams per mole. And in fact, since it's just times 0.10, I could just move the decimal point over. So 4.20 grams of C3H6. That would answer the question if I had phrased it properly. That's how much limiting reactant. And let's check out our two products. So CO2. Now these we've done enough that you might even have memorized. 5.19, this is moles, times how many grams per mole. For CO2, it's 44.01 grams per mole. Which comes out to 228 grams. By the way, I think I noticed one thing. Yeah, I should only call this 4.2. It's tricky. Normally we work in 3 sig figs, but because we did subtraction, you keep the 0.10, limiting me to 2. Okay, so 228 grams of CO2, and for water, it's 5.19 times the molar mass of water, which is 18.01 grams per mole, or 02 grams per mole. 5.19 times 18.02, 93.8 0.5 grams H2O. Okay, and that's how we solve this problem. So you can definitely expect one of these on the test, on the quiz. It's going to be like a 34-point thing, so call it what you want. You can expect one of these, one or two of the previous ones, and that's about it. Okay, thanks for watching.